Hello, this video is an introduction to my EMG project. EMG stands for electromyography. It's a measurement of the electrical activity of your muscles. So when your body wants to make a movement, your brain will send an electrochemical signal to the motor neurons in your spinal cord, which will then connect them to the motor units in your muscles, which will twitch and move your muscles. You measure EMG using electrodes, and the electrodes pick up the electrical activity from the muscle twitches. So looking up EMG properties, this quick Google search tells me that an EMG signal amplitude lies between 1 to 10 millivolts and a frequency range of 0 to 500 hertz, with the most dominant being between 50 and 150 hertz. So I've looked this up on other sources, and it says that 99% of the power lies between 50 and 500 hertz. So just keep that in mind further on. So the overall goals of this project: number 1, to obtain the EMG signal. Number 2, gather metrics about the muscles from it. So there's a couple of things. In general, people have different proportions of slow twitch to high twitch muscle fibers, and you can see that difference in the EMG spectrum. You could also see how the spectrum differentiates between different activities, and also how it changes over time. For example, let's just say you're holding a 20-pound box, like just straight in front of you, arms straight. At the beginning, it'll be really stable because you're using slow twitch muscle fibers, which fatigue less and are slower, so that's more stable. But as time goes on, your hands will start to shake because the slow twitch fibers are running out of energy, and you have to engage the high twitch fibers instead. And you should be able to see this change in the EMG frequency spectrum. This is my block diagram, my basic block diagram for the entire system. So you have some electrodes connected to some of your muscles. At minimum, you need 2 per muscle, which goes to a front end, which filters it between 50 and 500 hertz, and then amplifies it with a gain of around 500 to 750. Although this value's not set in stone. I'll just say that. And after that, it goes to an ADC, which does its magic. The electrodes, the ones that I'll be using, are just your classic ECG electrodes, which are most commonly made from silver chloride. And they're good because they have a pretty low half-cell potential, which is important because it means they'll have a lower mismatch between the electrodes. So usually the first stage of a bioinstrumentation system is an instrumentation amplifier. So if there's a large DC offset between them, that offset will get amplified up to however what's the gain is. And you want a high gain because with a higher gain you'll have a higher common mode rejection. So you need a low mismatch between the electrodes. The electrodes that I decided to go with are gel electrodes. They come pre-packaged with a set of gel, and they're disposable. Of those, I decided to go with tab electrodes instead of the kind of circly ones, just because I found the tab ones are easier to pull off. I've used the circle ones before, and they've just taken a giant chunk of hair out of my skin, and it's very painful. So the tab ones it is. So for the filter set amplifier section, there's 4 main parts. The instrumentation amplifier, the high-pass filter, low-pass filter, rectifier. Pretty simple stuff. The first stage in the filter and amplifier section is an instrumentation amplifier. Inside has 3 op amps with a bunch of resistors connected in between, which give it a high input impedance and high common mode rejection ratio. I have no idea how anyone would come up with this circuit, but they must have been smart. Anyways, a high input impedance reduces the impedance variation between the electrodes. Having a high common mode rejection ratio reduces the common mode noise. The most prevalent of this is from your mains power supply. So in Canada, the frequency of the mains power supply is 60 hertz. So if you're working in a room with like a lot of equipment, with a lot of outlets, there'll be 60 hertz EMI floating around all around you, and it can easily transfer to your skin. And in a lot of cases, the amplitude of the noise can be larger than the signal itself. So having a large common mode rejection ratio reduces this because the noise should be the same anywhere on your body, or anywhere on your skin at least. Filters, I mean, I don't know, it's pretty standard. 50 hertz high pass, 500 hertz low pass. Probably just like, I put minimum second order, mainly because I've seen like other things like the MyoWare EMG thingy, and I mean they used for their low pass, they used an integrator or like a low pass filter, first order low pass filter. So I was just kind of like, make everything second order. I mean, I could do higher order, but I don't. But it could require more parts. So I was just like, I want to minimize parts, but still be kind of good. So second order, let's do it. For the ADC, there's not really much to say. Just minimum 12 bits. I don't even know if you can get lower, but whatever. 12 bits, probably 16, whatever's cheap. I'm a broke college student, so yeah. The rectifier, I just found this design guide by TI. I'll put a link, maybe. I don't know. Sure. I just kind of copied it. I mean, it's a full wave rectifier. I mean, you could probably do it digitally, which, I mean, wouldn't that just be like an absolute value function? Which is, yeah, that's way easier. It uses less components, so, yeah, sure. I mean, I already did it, so I'll just use the full wave rectifier, but it's a good backup. If I need to, I'll just use a absolute value function software. Well. So the actual circuits I'll probably go over in the next video if I do it. If not, well.